So my talk will be a little bit different. My expertise, I'm a mathematician, but working on that kind of maths used for real-world applications. So, for example, my first postdoc was at the Euro-Mediterranean Center on Climate Change, working on operational oceanography. So, sorry for my cut. Actually, what I'm going to talk today, I'm trying to face a few points about the data we have. For example, especially the last talks and also the previous one, they mentioned all this data we have from satellites, from sensors, a lot of data we have. So what I'm not going to talk here is that also for sensor and all the sources of information that we have, we work on machine learning technologies for placement of these sensors. Because sometimes, depending on the position of the sensors we have, we can have useful or not useful data. Assuming that we did already that and we have these good data, so we can try to figure out something from the data we have. So we want to predict something. And the point is that these predictions usually are not accurate enough. So we use machine learning and data assimilation technologies to improve the prediction of the real-world application we are going to train. How to have this real-time prediction? For example, in oceanography, imagine that you are trying to predict a storm. You want to predict the storm in a real time, almost real time. Operation centers work on this big system of equations, partial differential equations. They solve that on supercomputers, but even if they are super efficient, very quick, a lot of nodes, big computers, it's very difficult to reach real-time prediction, so to be active when something is really happening in a real case scenario. So what I'm going to talk is about this point. So when we want to do something quickly, we want to predict something in a real time, when for me real time means the reasonable time that you can use to act to do something. So it depends on the scenario. And also we face the problem of big data, as they showed before me and as I'm going to show. All this information produces a lot of data. So the technologies I'm going to focus here, actually in this talk I will focus on ocean, but can be also applied to a lot of different real-world applications. Especially probably interesting for you is engineering, so robotics, and also for fake news related to the last slide of the previous speaker, or finance. Anyway, are very general, so can be applied almost to all real-world application. I will show you. So actually, I can really link to the last slide of the previous speaker, because what I want to say here is that we have all these sources of information, and actually not only from the ocean, because how it works now in operational centers, you have your oceanographic model, this big system of PDEs, blah, 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 but you have couple models, because we studied that the interaction with the atmosphere is one of the main points, the important points. So what we work on is not only ocean, but like a coupled model between ocean and the atmosphere. And all these models are like, actually now we are really able to have these really fine grids for modeling stuff. But this means having more data. So the problem we are going to face are big data problems. There is no point. So when you have so many problems, so many data and so many different kind of data you want to put together, there are too many possibilities to face the problem. One is simplifications. And usually also in operational sensor, we introduce a lot of simplifications because we cannot face the problem. So sometimes simplification can be only just decide which kind of data you want to use. Not all the data, only some of them. Or another approach can be the decomposition of the domain, which is something I'm going to talk about. So talking about the reduction. So, for example, this is a simple test case. I'm going, at the beginning of the talk, I'm going to focus on simple test case because this is the way we develop the technologies. We focus on simple test case that we can manage completely, we can control completely, both from the numerical point of view and in the laboratory. And then when the technology is stable, we apply the technologies to real case scenarios. So I will show you also real case scenarios. But this is, for example, a shallow water model using a software, numerical software, solving a system of PDEs. So on the top, you have the computational fluidodynamic result, and on the bottom, you have something that we call reducer the model. Reducer the model is a model, essentially how it works. You use the data from the computational fluidodynamic model. So you need a computational fluidodynamic model in this sense. This is the reason why we are friends of people working in operational centers on the system of PDEs, because we need also that data. You train your model. You reduce the space depending on the variance that you want to include in your data. In this case, with 29% of the variance, we are assuming like you have to consider that on the top we have like 10 million of points nodes. On the bottom we have only the reconstruction given by 20. Only 20. This means that, but if you check, we can have almost the same. This is a reproduction. So the same reproduction of what the computational fluidodynamic is able to do. This is with machine learning on the bottom. On the top is the computational fluidodynamic. The computational fluidodynamic takes to produce this quick simulation. It looks quick, but it takes like 0.6 hours. The bottom is only 0.001 hours, which means few seconds. But this is a reconstruction. What if you want to use that for a prediction then? We can do that as well. So we studied how then, as soon as we have this model and this model defining this reducer space, we train a neural network, and we try a proper neural network, in this case a neural network called long short-term memory neural network, which is able to train temporal sequences. And then we use the neural network to predict something. And we can have our prediction in real time with a good accuracy. But this is like a toy case. What when we go on a real case scenario? When we go on a real case scenario, the even small differences in the results of the model can be propagated in the real case scenario in completely destroying the result. So it means that even if you have real-time simulation, real-time predictions on even very big supercomputers with machine learning, if you don't have accurate predictions, it's useless. So what we do to have real-time prediction but with a good accuracy, to do that we use data assimilation. If you Google it, there are so many different definitions of data assimilation depending on who is working on that. In operational, you probably find a computationally very intensive problem, or just a data filtering problem, or anyway, big data problem. So what we assume for data assimilation, this is a quick video.
We are all familiar with the butterfly effect. A small change in weather in one part of the world can have huge consequences in another. How can we detect such changes early on so that we can act better and sooner? Scientists are developing numerical models that deal with this uncertainty and make forecasts more accurate. They do so using data assimilation, a methodology that combines observed measurements and numerical predictions. Take a weather forecast. Using an initial data set of temperature and air pressure measured in a region, researchers develop a numerical model that predicts how they will change. This is challenging because airflow is chaotic and many variables need to be included in the model to predict this change. This also means that the model's prediction will have a high level of uncertainty. To limit this uncertainty, real-time data is collected and input, or assimilated, into the model. Researchers observe how much the real situation differs from their numerical model and adjust it to make the forecast more accurate and reliable. The maths behind data assimilation can be applied to a variety of research topics, from atmosphere and climate changes to vehicle design and health management. The Data Assimilation Laboratory is just one of the multidisciplinary labs that make up the Data Science Institute. To find out more about our work, visit imperial.ac.uk/data science.
So, what data assimilation is then? You have your data. You use your data as initial condition for your forecasting model. That can be your machine learning model or your system of PDEs, your forecasting model. Assume that like a black box. And then you have your results in a time step which is after that. What data assimilation do, assume that you have also other sources of information, different, also completely different, but that you can combine. We call that observed data. Data assimilation put together these two informations, producing a third value, which can then given like input of the forecasting model to produce another forecast, which is more accurate. Why this happens? Because actually, your model, there are a lot of errors that we cannot really reduce. For example, the only fact that you are using a system of equations, so you are modeling with math, something which is in a real world. So this is the first approximation. Then usually the equations are defined in a continuous space, but when you want to solve that on a computer, you cannot solve that on a continuous space, so you have to discretize, you have to consider only discrete points, another level of simplification. Third level, when you solve something on a computer, you have a lot of error in the chips, which are usually altogether called random errors. So all these error propagates to the input data through the model in the solution. This is the reason why we cannot have a good weather forecast, the main reason. So what we can try to do is to improve what we can improve with data assimilation, which is the initial condition. Imagine if you can do that quite often. As much as you adjust your initial condition, as much as you can improve your forecast. The Met Office, for example, do that every 6 hours for their models. But this is because the model is quite slow and some kind of observation are only available every few hours. But imagine if you can do that every hour or even better, every 10 minutes. You can definitely improve the quality of the forecast. The point is that, so if you, for example, considering the previous example, if you have the model predicted by the computational fluidodynamic and then the reducer of the model, and then assume an observation that in this case is a reconstruction of a picture. This is for one of the projects we have in which we try to assimilate data from picture made by drones. The problem with drones instead of satellites is that when they take a picture, you have an angle, and that angle should be considered when you try to assimilate data, because it's like it's quite big. It's not like for satellites that are so far that is like we are on a plane. For drones, we are not a plane, so there is a lot of pre-process to do on the data. So as you can see on the bottom, this is the machine learning with the data assimilation inside, which is closer to the observation with respect to the forecasting. Just to mention a real case scenario, how this can work in a real case scenario. This is for the north of Brazil. So you use all your simulation, you build your network, and then you try to reconstruct the full space. When you do that with data assimilation, you can see in the bottom right the result of data assimilation with neural network. On the bottom left, the result from my ocean. On the top is the prediction of the data assimilation. So on the bottom right is the error. On the top left is the prediction with data assimilation and neural network. If you compare with my ocean forecast, it is quite close, but the point is that if you compare that with the my ocean forecast and the SSH provided by Aviso, then you can see that the neural network with data assimilation is quite close to the real observations. So this fusion that we are trying to have between the model and the observation actually works. This was the first possibility. What about the second, the use of decompositions? You can have, imagine you have a geographic distribution and then you want to solve the problem. You can, like simply imagine, you can decompose geographically your region. But what it means, just to make a simple example, not math, imagine you have a pile of papers to control. And then you have, like, you take part of this pile and you give the part to one person, which usually not happy to do that. And then you take the second part and you give the second part to another person and the third part to another person. But depending on what they have to check, for example, if there is a word ocean in all the papers, or if there is a sentence, or how many details they have to control in the papers, they have to communicate. So on the right hand side there is what we call domain decomposition. On the left hand side there is what we call parallel computing. Parallel computing is like several computers working in parallel on that. Why I underline this point of talking? Because this talking takes time. So when you are like an expert of domain decomposition of parallel computing, you can imagine it's quite simple. I decompose geographically the region, I give sub-regions to different computers, I try to solve the problem independently, then I start the communication because the salinity there needs to know the salinity on the other side, then a lot of correlations and blah blah blah. So all this blah 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 takes a lot of time in terms of computational. So we are trying to phase to reach real-time executions, and then we start to communicate among all the nodes of the computer all the time, and it's useless. So what we usually, the approach we use, these parallelism can be introduced at several levels of the math stack. This is called math stack. So from the real world to the system. So usually what happens is very common. People have a software and they start to introduce libraries for these to solve the software, to use the software in parallel on a GPU or a cluster of CPUs, anyway, on big supercomputers. This doesn't work because you introduce a lot of communications. What we do, we know that these parallelism should be introduced at the beginning. So in the physical problem, in the mathematical problem, this is what we do. To do that, you have to reformulate completely your mathematical model. And this is how we face the point. So one application of that, this is the Caspian Sea, for example. We did this application for almost all the enclosed and semi-enclosed seas. This is the Caspian, but also for the Mediterranean Sea and the others. So for the Caspian, for example, we decompose the domain in slices because this is one of the importance of the multidisciplinarity. From the physics, we knew that in the Caspian Sea, we have a very big difference between north and south in terms of both temperature, salinity, different conditions. Even during winter, the north part is freezing, the south never. So all this information, we use all this information to decompose properly the domain, in this case, so in slides, in horizontal slides. On the right hand side, you see the decomposition made of 10, 12, 20, and different kind of decompositions. But the Caspian Sea is quite small. What if we want to do that for a big case, like no the Mediterranean Sea or Caspian or whatever, but a big ocean? We do that using domain decomposition, but on big supercomputers. One of the supercomputers we use is in China. The name is Sunway. It has more than 10 millions of cores, and actually at the moment is not the first of the top 500, which is the classification of all the supercomputers worldwide. This year, since half of past year, the first of the top 500 is a supercomputer in US, but probably next year China will be the first again. So this is what we do. We use these kind of facilities with machine learning and data assimilation technologies to have predictions in quite real time. And thank you.
Thank you, Rossella. So we do have time for questions. There's one. Thank you. Otherwise, I'd
Rob Mosley downtown. I'm just wondering if you see kind of how much resistance you see to using machine learning in your networks from operational model operators, I guess, traditional models. Yeah, what is resistant from traditional model users?
From the people or from the model?
From the people.
From the people, if I can be honest, they don't see machine learning like a good friend. But actually, it is because the way people try to sell machine learning is not the good way. I always say that we don't want to replace the physical models. The physical models, for example, with machine learning, another point that I forgot to say, with machine learning, when you train a network on some data, and in that data there were not any prediction of something new, like I don't know, a new storm or whatever, something from Lorentz, from the chaos theory, you cannot predict that with machine learning because you didn't train that. This is the reason why we combine with data assimilation, because using the data assimilation we can try to have physical meaning of the machine learning. But the community is not ready yet. So it's like there is like a big gap between two communities that don't really want to communicate each other. So we are trying, we are starting. It's simple for me because I'm from the operational center, so I work on system of PDEs. I work on NEMO and NEMOVAR. So I'm from that kind of systems, and then I moved on machine learning. So for me, it's quite simple because I am in the middle. But when I try to talk with people working in the operational, they are like, they don't want to see about it. So yeah, not yet. But I know that the ECMW is working on machine learning. They have a machine learning version of the weather forecast. They have it also for ocean. So they have a group working on that.
Okay, is there only one more quick question? If not, then one more, as long as it's quick. And the answer has to be quick as well.
So, it's very, very impressive work there, and what I can see is an ever-increasing need for onboard sensors and instrumentation on actuators on marine projects. And what I was wondering is, how long before this type of machine learning skill set is mainstream, and how will today's school leavers require it at some stage?
But actually, one of the main problems with math in general, with models in general, is that you have to be really efficient, you have to customize your model on your application. So probably there are already tools. We are already ready to provide tools and stuff for projects and for operational stuff. But they are not efficient. This is one reason why people from operational centers don't want to accept that it could be powerful. So yeah, with projects, you have to start from scratch, understanding which kind of model you want to build, which kind of machine learning model you want to build for which kind of problem. So there is nothing yet about that.
Okay, so thank you again, Rossella.